Hi everyone. So in this video we introduce a very important concept that's very common in optimization for training deep neural networks, which is momentum. And the idea of momentum is very simple. So basically it's an adjustment of the concept of the learning rate, right? So instead of taking a parameter update step that's solely governed by the direction of the negative gradient, instead of thinking of the negative gradient as basically the sole governor of the next parameter update step, no, we think of it as basically a force that pushes the parameters in a certain direction. But these parameters already should the parameter update should have a momentum from the past updates, right? So remember the example that we had about the cliff, right? So here I have a gradient that tells me to move in that direction. So I have a one-dimensional, right? So in that direction, and once I go up here, right, the gradient suddenly goes in the other direction. Now, because before we were assuming that you just move in the negative gradient direction, whatever that direction is, right? So we had this danger that that maybe you can undo a lot of steps that you have already done before, right? Now with momentum, the more moves I do in that direction, in the left direction here, right? So all these steps, the more I gain momentum in that direction. And whenever the force changes, right? So think of it as a physical object. Every time the negative gradient is pushing that object in a certain direction. And that object, assume that object has unit mass, right? So the velocity is the same as the momentum. So that object moves with a certain velocity, right? That velocity increases as we push it more in the same direction. If I push suddenly in the other direction, then that decelerates or even moves the object in the other direction, but with a slower speed than if I just took the gradient as the only factor that determines the parameter update step. Right? So it's a very simple concept. How is it applied? It's applied by basically taking the current momentum, V here for velocity, because we are assuming the analogy to a physical object that has unit mass, so momentum would be the same as velocity. So we update V by a factor alpha times the past V, right? So this is an exponentially decaying accumulation of past gradients, right? So every time I multiply the current momentum by alpha, and then and I add that to the new momentum, right? So and then that contribute to the new momentum. So the new V is alpha times the past V, right? So this is the new, and this is the old. So the new V is alpha times the old V minus epsilon, which is the learning rate, times the gradient. Right? So epsilon g here, this is the SGD gradient update. And alpha V is the momentum, right? And then you update the parameters theta by theta plus V, right? With the current update value. So the current update value depends on past update values. Now, one thing to note when momentum is used is that basically, so let's say I'm moving along a line, the gradient is consistent, right? So then I'll keep pushing in that direction, right? So every time I push in that direction. Now we note that this will keep increasing the momentum in that direction, right? So if the gradient is consistent, we have to note, if the gradient is consistent, so V equal alpha V minus epsilon G, right? And this V new has the same direction as V old. So I can basically say that V times 1 minus alpha equal epsilon G, right? And then the size of the step, right, becomes epsilon times the norm of g, the norm of the gradient, divided by 1 minus alpha, right? So v here equal epsilon g over 1 minus alpha, right? So the norm of v equal epsilon times the norm of g over 1 minus alpha. The size of each step is given by epsilon times the norm of the gradient, which was, so this would have been the size of the step with SGD. Now we divide by 1 minus alpha. So if alpha is 0.9, for example, then the step size is 10 times that of SGD. So maybe, so if the gradient is consistent, if you are navigating a parameter space where the gradient is consistent most of the time, then the learning rate has to be adjusted because I take much larger step with momentum. And typically alpha is initially small, right? Because why? Because at first we want to explore. We don't want to be affected by past gradients. Because at first I'm assuming I'm nowhere close to a good solution, so I want to explore as much as possible of the parameter space. So at the start of training, alpha is initially small, and then is later increased because then history becomes a dominant factor in the optimization, right? So that's why alpha is later increased, because later I assume that I am close to the optimal solution and I don't want to leave that region just because of the value of one gradient, right? Or the direction of one gradient. And common alpha values in practice, so this is just an empirical observation, include half, 0.9 and 0.99. And again, it's very important to keep in mind that if the gradient is expected to be consistent in a large region close to the good solution that we are looking for, then the learning rate has to be adjusted because momentum will increase the step significantly. Thank you.